445 million years ago, the ocean did something it has only done a handful of times in the entire history of this planet. It killed almost everything in it. Not with fire. Not with an asteroid. Not with poison gas boiling out of the crust. It killed almost everything in it with ice. If you watched our last video, you already know what a runaway extinction looks like. Heat trapped the world in a furnace it couldn't escape, and something like 90% of life on Earth suffocated in it. This is the same planet. The same basic physics. But this time, the runaway ran the other direction. The cold didn't just arrive. It fed on itself, got worse and worse and worse, until the shallow seas that held almost all complex life on Earth were strangled by their own climate. This is the Late Ordovician extinction. It is the second deadliest event in the fossil record. Roughly 85% of all species alive at the time were gone by the end of it. And for a long time, scientists assumed an ice age should be gentle, slow, survivable. This one wasn't. By the end of this video, you'll understand exactly why a falling thermometer can be just as lethal as a rising one, and why this particular ice age is one of the strangest, most counterintuitive disasters in the deep past. To understand how strange this event was, you have to understand what Earth actually looked like 450 million years ago, because it is almost nothing like the planet you're picturing. There were no fish with jaws yet. No plants had colonized dry land in any meaningful way. The continents were essentially bare rock and mud. Silent. Empty. Alien. But the oceans were the opposite of empty. The Ordovician seas were arguably the most biologically rich the planet had ever produced up to that point. Reefs built not from coral as we know it, but from sponges and calcifying algae stretched for enormous distances. Trilobites crawled the sea floor in hundreds of distinct forms. Nautiloids, some of them growing shells over 6 meters long. Hunted as the apex predators of their age, drifting through warm, shallow seas that covered most of the planet's low latitudes. This was a world running almost entirely on marine biodiversity, concentrated overwhelmingly in shallow continental shelf waters. That detail matters enormously, and you should hold on to it, because it is the single biggest reason this extinction turned out to be a mass casualty event instead of a survivable cool-down. This was not a sparse, struggling biosphere. This was arguably the single greatest explosion of marine biodiversity the planet had seen up to that point. A period paleontologists now call the Great Ordovician biodiversification event. The number of marine families roughly tripled over about 25 million years. Brachiopods alone diversified into hundreds of distinct forms, filter feeding across the sea floor in numbers hard to picture today. Crinoids, animals that look like plants but are closer relatives of starfish, turned huge stretches of shallow seabed into something resembling an underwater meadow, swaying stalks packed shoulder to shoulder for as far as the eye could see, if anything back then had eyes capable of seeing that far. Global temperatures at the time were also significantly warmer than today's average. Carbon dioxide levels were high. By most reconstructions, this was one of the warmest, wettest stretches of the entire Paleozoic era, which makes what happened next feel almost backwards. Something changed on the southern supercontinent of Gondwana. As it drifted directly over the South Pole, ice began to accumulate. First, as isolated highland glaciers, then as something much bigger. And this is where the runaway feedback kicks in. The same mechanical trap you heard about with the heat-driven extinction, just running in reverse. Ice reflects sunlight. Bare rock and ocean absorb it. So as the Gondwanan ice sheet grew, it reflected more of the sun's energy straight back into space, instead of letting it warm the planet. Global temperatures dropped further, which meant that colder temperatures could allow more ice to form and survive. This, in turn, meant more ice reflected more sunlight. And more reflected sunlight meant an even colder planet. Scientists call this ice-albedo feedback, and once it starts, it doesn't need any outside push to keep accelerating. The system feeds itself. Within what may have been a remarkably short window. Some estimates put the core glaciation event at under 1 million years, a geological eye blink. Massive continental ice sheets locked up an enormous volume of the planet's water. And when that much water gets pulled out of the ocean and frozen onto land, sea levels do not recede gently. They collapse. Estimates suggest global sea level dropped somewhere in the range of 50 to 100 meters during the peak of this glaciation. Picture that against everything you just learned about where Ordovician life actually lived. Almost the entire biosphere was concentrated on shallow continental shelves. Warm, sunlit, food-rich water measured in tens of meters, not open ocean depths measured in kilometers. A sea level drop of that scale didn't just shrink those habitats. In huge areas, it erased them completely, turning thriving reef ecosystems into exposed, dead seafloor almost overnight in geological terms. This is the piece that surprises people every time they learn about this event. We picture ice ages as slow and survivable because we're used to thinking about them the way modern humans experienced the last one. Gradual, over tens of thousands of years, with time to adapt. The Late Ordovician glaciation didn't offer that kind of runway. The habitat that 90% of complex life depended on physically disappeared out from under it. But the ice sheets weren't finished. A second, compounding disaster rode in right behind the first one, and this is the part that turns a bad extinction into one of the worst in Earth's history. As the oceans cooled and sea level dropped, ocean circulation patterns were violently disrupted. Cold water sinks. Warm water rises. Under normal conditions, this circulation constantly recycles oxygen and nutrients through the water column. But the sudden reorganization of ocean currents during the glaciation appears to have triggered widespread ocean anoxia. Vast stretches of water, starved of dissolved oxygen, in the aftermath of the initial ice-driven habitat collapse. Think about what that meant for anything that survived the first wave. You've already lost most of your shallow water habitat to the falling sea level. Now the water that remains, in many regions, can no longer support animal life at all. It's a 1-2 punch. First, the world takes away where you live. Then, it takes away the ability to breathe in what's left. This is why researchers increasingly describe the Late Ordovician extinction not as one event, but as two closely linked pulses. A glaciation-driven habitat collapse, followed by an oxygen crisis in its wake. Trilobites, brachiopods, graptolites, early jawless fish, and the reef-building organisms that had defined Ordovician seas for tens of millions of years were hit in both waves. Some groups, like the massive nautiloid predators, never fully recovered their earlier dominance. Entire reef ecosystems essentially vanished from the fossil record and would not be rebuilt in anything like their previous form for millions of years afterward. The graptolites are one of the clearest casualties in the entire fossil record for this event, and they're worth pausing on. These were small, colonial, floating organisms. Not dramatic to look at, but they were everywhere, drifting through open ocean water in staggering numbers, and their remains are so common and so distinctive that geologists use them to date entire rock layers around the world. Across the Late Ordovician boundary, whole graptolite lineages simply stop appearing in the rock. Not dwindle. Stop. That kind of sharp, clean cutoff in the fossil record is exactly what you'd expect from a genuinely fast, genuinely brutal extinction pulse, rather than a slow background decline. Here's what makes this extinction genuinely strange, even by mass extinction standards. Most of the other major extinctions in Earth's history line up cleanly with an obvious trigger: a massive asteroid impact, or catastrophic volcanic eruptions pumping out greenhouse gas for tens of thousands of years. The Late Ordovician event has no smoking gun like that. There's no giant crater, no matching layer of eruption-driven rock spanning the globe. Instead, the leading explanation is almost unsettling in how ordinary it sounds. A continent drifted, by pure tectonic chance, into the right position to accumulate ice at the pole. And an already cooling climate crossed a threshold that let the feedback loop take over on its own. No external trigger required, just the planet's own systems tipping past a point where they could no longer self-correct. That idea, that a mass extinction can happen without a dramatic external cause, purely from the planet's climate crossing an internal tipping point, is part of why scientists keep coming back to this event. It's a working demonstration that runaway feedback loops don't care which direction they run. Push global temperature up past a threshold, like you saw in the extinction we covered last time, and you get a runaway greenhouse. Push it down past a different threshold, and you get a runaway icehouse. Same planet, same vulnerability, opposite direction, nearly the same body count. There's also a timing detail that makes this even harder to pin on a single dramatic cause. Some geochemical evidence suggests carbon dioxide levels may have already been dropping in the millions of years leading up to the glaciation, possibly tied to the explosive growth of early land plants and increased rock weathering, pulling carbon out of the atmosphere faster than usual. If that's accurate, it means the trigger wasn't even a single event at all. It was a slow background shift that quietly set the stage, followed by a tectonic coincidence that pushed the system over the edge. Nothing about it needed to be violent, to be devastating. Life did recover, eventually. As the glaciation ended and the ice sheets retreated, sea level rebounded, oxygen returned to the water column, and shallow marine ecosystems slowly rebuilt themselves over the following several million years. Some of the survivors would go on to give rise to entirely new evolutionary lineages that hadn't existed before the crisis. Extinction events, brutal as they are, tend to clear space for whatever comes next. But the recovery came with a twist that a lot of people find genuinely unsettling once they hear it. The end of the glaciation was itself another rapid climate swing. This time warming, as the ice sheets melted and sea levels rose back up over a relatively short window. So the organisms that had just survived one of the fastest cooling events in the fossil record were immediately handed one of the faster warming events right behind it. Some researchers now argue that this second warming-driven pulse compounded the damage from the first, rather than simply reversing it. In other words, the planet didn't just get hit with an ice age. It got hit with the ice age, and then with the whiplash of climbing back out of it, in a geological instant, twice in a row. But here's the detail worth sitting with as we close this one out. Two of the deadliest events in the entire history of complex life were driven by the exact same underlying mechanism. A climate feedback loop that once triggered ran away from equilibrium and didn't stop until it had reshaped the planet. One ran hot. One ran cold. Both nearly ended everything. Which raises an obvious question. If a feedback loop like this can trigger from something as mundane as a continent drifting into the wrong spot at the pole, what happens when the trigger isn't tectonic drift over tens of millions of years, but something far faster? That's where we're going next.